The next several videos are going to cover Chapter 16, which is about additional aspects of equilibrium we haven't covered already. The primary focus of this video will be covering buffers, what they are, and how effective they can be. So the first question we must ask is, what is a buffer? Well, a buffer is a solution that resists changes to pH. That is, when you add an acid or base to a buffered solution, the pH doesn't change much depending upon how much acid or base you add to it. Buffer solutions are composed of weak acids and bases and the conjugate ion of those weak materials. If you don't have a weak material, then you don't have a buffered solution. That is, using strong acids and bases, you cannot create a buffered solution. But you must have both the weak acid and base and its conjugate ion. It's not enough to have just one. Now, here are three potential buffered solutions. Can you guess which one isn't going to be a buffered solution? Well, the first example is a weak acid and its conjugate ion. And we know that because it's not one of our 7 strong acids. We see that they both have a common ion in effect, that is the C2H3O2, and therefore, being weak and having a conjugate ion of the weak acid, this creates a buffered solution. Number 2 is formed from nitric acid and sodium nitrate. This is not a buffered solution because nitric acid is a strong acid, and even though it has a conjugate ion there, strong acids do not have equilibrium constants that are less than 1, and therefore this would completely dissociate into water. Situation 3, ammonium chloride and ammonia, is a buffered solution. They both have NH3 in common. That is, the weak acid, or the conjugate acid of ammonia is the ammonium ion. And so it's important for us to recognize ions that come from weak materials. If you're not up to date on that, that's something you'll want to go back and review. Now, when we make buffered solutions, we want to make sure that they're capable of handling realistic amounts of acid and base when they're added to them. That is, we don't want a flabby little buffered solution. We want it to be able to withstand some change of significant acid or base addition. So what do we do to make a buffer, and how do we make sure that it can resist a change to pH? Well, like we said, that the addition of a weak acid and a conjugate ion of that acid or base is what is needed to make a buffered solution. Now, the pH of the buffered solution is dependent upon the pKa, which is the negative log of the acid dissociation constant for that particular ion. So, for example, lactic acid, which has an acid dissociation constant of 1.4 times 10 to the minus 4th, or has a pKa of 3.85, is effective at making buffered solutions ranging from 2.85 to 4.85. Now, having said that, this becomes a better buffered solution if we try and keep our pH as close as possible to that 3.85 value. So we do have a range to play with when it comes time to making our buffered solutions and what ions we can use to create them. So they do have a working range, but the closer the pH that you want to get or desire to make is to the pKa of the material you're using, the better the choice it's going to be. Now, when we talk about making buffers, we have buffering capacity. And that is how much material is used to make the buffered solution. That is, how many moles are present. The more moles of each acid and conjugate ion or base and conjugate ion present, the longer it's going to be able to resist changes to pH. Therefore, we're really just talking about buffering capacity being a number of moles issue. That is, moles of both acid and or base with its conjugate ion. So here I've got 3 different potential buffered solutions, and they are all potential buffered solutions. They contain a weak acid and its conjugate ion, that is lactic acid and sodium lactate. Now, the first example there, the 0.12 and 0.1 molar solutions of lactic acid and sodium lactate, is a good buffered solution. It is got approximately equal amounts of both acid and its conjugate ion, so it will resist changes for a while. However, it won't last nearly as long as the second case, simply because it's got a higher concentration or more moles in it. The third case, however, we have a radically different concentration between the moles of lactic acid and the sodium lactate. And so while this is a buffered solution, it's not going to have a very good buffering capacity because it's going to run out of sodium lactate first if we're doing a neutralization reaction, which will be the focus of the next video.